This video covers some miscellaneous reactions of aromatic compounds. We can oxidize at the benzylic position using potassium permanganate to get the corresponding benzoic acid. Notice that in this case we have cleaved this carbon-carbon bond and we end up with only one carbon remaining. In the case of toluene, we also end up with benzoic acid. In order for this reaction to occur, we need to have at least one benzylic carbon-hydrogen bond. In this case, for ethylbenzene, we've got 2 carbon-hydrogen benzylic bonds. Here we've got 3 benzylic carbon-hydrogen bonds. And so these can be cleaved and oxidized with potassium permanganate to give you the carboxylic acid. Nitro groups can be reduced, regardless of whether they're on an aromatic ring or not, to the corresponding amine. The reagents that we can use for this is either hydrogenation conditions with hydrogen, nickel, or palladium as a transition metal catalyst. We can use tin and hydrochloric acid, or we can use iron and hydrochloric acid. In each of these cases, we're doing a functional group transformation from a nitro group to an amine. We can reduce aldehydes and ketones to the corresponding alkane. Now, both these reductions are not specific to aromatic ketones. They will work just as well on other ketones and aldehydes. The first example is the Wolff-Kishner reduction. This is under strong base conditions, and we use hydrazine, potassium hydroxide, and heat in order to completely cleave this carbon-oxygen bond and get the corresponding alkane. We can also do the Clemmensen reduction. In this case, we end up with the same product, which is complete reduction of the ketone to the corresponding alkane, but now we're doing it with zinc-mercury amalgam and under strong acid conditions like hydrochloric acid and heat. Both these reactions utilize very harsh conditions. You choose which reaction you want based on whether you can use a strong base for your substrate or whether you can use a strong acid for your substrate. This reaction will not work for carboxylic acids and their derivatives, only for aldehydes and ketones. We can also halogenate at the benzylic position using NBS in the presence of light or peroxide like hydrogen peroxide. In this case, as long as we have a carbon-hydrogen benzylic bond, we can put in a bromine using NBS. Remember, some of the common peroxides that you can use are hydrogen peroxide, tert-butyl, hydroperoxide, and so on. This will also work for allylic positions. So if you have an allyl group, you can use NBS and let's say hydrogen peroxide and get allylic bromination. Deuteration also undergoes an electrophilic aromatic substitution mechanism, and in this case we are substituting a hydrogen with a deuterium using deuterated sulfuric acid. If we use excess deuterated sulfuric acid, we can deuterate every single position on the aromatic ring. We can also do iodination using iodine and nitric acid. Here, nitric acid is acting as an oxidizing agent, and it oxidizes iodine to the active electrophile. And finally, just like we could do a sulfonation, we can also do a desulfonation. If we treat a sulfonated aromatic ring with water and heat or steam, we can remove the sulfonyl group and put back a hydrogen. Now pause the video and predict the major products of the reactions before moving forward. In the first example, we've got an aromatic ring with a tert-butyl group, a methyl group, and a nitro group. The first step involves treating it with potassium permanganate. We know that potassium permanganate can take any benzylic CH bonds and convert it to a benzoic acid. So that means we're going to convert this into a benzoic acid because we've got benzylic CH bonds here. Now remember, nothing happens to this tert butyl group because it's fully substituted and we have no benzylic CH bonds. So after the first step, we're going to get a benzoic acid, the tert butyl group and nitro group remain intact. And then in the second step, you're treating it with tin and hydrochloric acid, and we're going to do reduction of the nitro group to the corresponding amine. So your final product has a tert butyl group, a carboxylic acid, and a corresponding amine. Later on, we'll see that both an amine and a carboxylic acid can react and cyclize. In the second example, we start with a diketone and an aromatic ring, and the first thing we do is a Wolff-Kishner reduction with hydrazine, potassium hydroxide, and heat. Here, ethylene glycol is just a solvent. And we're going to completely reduce and cleave these ketones. And so we end up with an aromatic ring and a carbon chain. So there are 1, 2, 3, 4 carbons, and so we can draw out the 4 carbon chain. After this, we treat it with NBS and a peroxide in dichloromethane, and here we're doing a radical halogenation at the benzylic position. And so we've got a benzyl bromide and the rest of the carbon chain. And at this point, we're treating it with DBU and THF. Now remember, THF is a polar aprotic solvent. DBU is a strong non-nucleophilic base, which means that it's perfect for an elimination reaction. So this is an E2 mechanism. We're going to eliminate this hydrogen and form an alkene. So your final product after these 3 steps is an aromatic ring in conjugation with an alkene and then 2 remaining carbons.